Welcome back, troops. Okay, what are we doing today? I'm going to talk to you about work done by a gas. Okay, there's a little formula there, you can see it on the screen. I want to show you how we arrive at that and what it actually means and when we can actually apply it. So let's move on. Here we go. First of all, what is work and how do we calculate it? You should know this from Key Stage 4, and we did it in mechanics. So I'm going to push ahead, have a think. You want to pause, but I'm going to push ahead now. So here we go. Essentially, work done is energy transferred. So in this case, there's a bloke here, he's pulling on some box with a force, and that box is going to move a certain distance. And we know that the more force and the more distance, the more work is being transferred from his muscles, the more work is being done. Very important, it's the distance moved in the direction of the force. We all know this previously. So that's basically work done. You know this, okay? Measured in joules, it's work done, it's energy. Okay? Now then, as applied to gases, let's give a little look back at Charles's law. Now, recall Charles's law, we have a fixed mass of gas. That gas is being heated gently so that it expands. And when it does expand, if we heat it gently, it will expand under a constant pressure. Okay? So in the experiment, we add heat, and the gas expands under that constant pressure, and we can measure that expansion, we can measure the increase in volume, and we end up with that relationship that we've looked at before. Okay, so that's what's actually happening. So how can it be expanding under a constant pressure, I hear you ask? Don't worry, kids, I will show you. Here we go, let's reset this. This is PHET. Look at the link at the top there, look at the web address, go to PHET. They've got lots of nice little simulations there. I encourage you to use them. So let's make this little box. Here we go. I'm going to pump some gas in. And as we look, this is representing the gas particles, and they're filling up the space, the available space, and they're impinging on the inside of that container. Now each impact imparts a little bit of force, which all adds up to pressure. So the number of impacts per second is indicative of pressure in this case. Now I'm going to set this such that the pressure is going to be remaining constant in this system, and I'm going to add some heat. So we can see the pressure is about 20 atmospheres. I'm going to add some heat. The gas is going to get hot. Okay, if the pressure remains constant, what happens is that the gas does some work to expand, and you can see it's pushing that left-hand side of the box. So I add some heat under this constant pressure, and it causes expansion. Now, if the box couldn't move, well, you can find out yourself. Have a play on this. PHET, good stuff. Okay, so that's what we mean by the gas doing some work. Okay, adding heat, and that heat is going into causing some work to be done, and the pressure is remaining constant. Okay, and you should be able to see that the volume over temperature, V over T, is remaining constant in this case. Okay, let's get rid of that. Let's go in a moment. I just get the magic camera up. We're going to go and look at how we actually get to that. Okay, let's do some whiteboard work, or in this case some paper work. Here we go. Right, now, so we know that work done is force times distance. We learnt that years ago, and it's still very important to know it now. So let's consider this scenario. I've got some sort of gas syringe or a piston, something in an engine, and here we go. Look at this 3D drawing I am drawing. Isn't it marvelous? Okay, so in here we've got some gas. Okay, and that gas has a certain pressure. Now, this is a plunger here or a piston, and that gas is impinging on that piston there, and that has an area. Let's call that A. Okay. Now in this scenario, we've got the force of the particles in this area, and that imparts a force here. Okay. Are we okay with that, campers? Good. So gas, pressure, plunger of a certain area, and then we end up with a force. So we come back a little while later, or we watch it happening in real time, which you can do when you do this in real life, and what has happened to the plunger, what has happened to the piston. It's actually moved a distance. Here we go, is my gas. Still under constant pressure. Constant pressure is important for this. Okay, same area. And if we look, we can see that the plunger has moved a distance. Should we just call that distance x? Okay. Good. Has some work been done? Yes. A force has moved this object a distance x. So let's write this down. The work done is equal to F times x. Super. What is that force? Well, we know from GCSE physics again that pressure is force over area. Force spread out over an area in pascals. If we rearrange that, we get force is equal to pressure times area. Happy so far? I didn't hear you. Yes, of course you are. Right, now we're going to substitute this value F, this, into this formula. So we end up with a new formula now, which looks like this. Work done is equal to pressure times area times by x. Okay, nearly there now. Let's have a look at what this means. This is an area. This is measured in meters squared. This is x. This is measured in meters. That is a volume. In fact, that volume there, AX, let's superimpose this on here. Can we see? That's where it originally was, and that's where it is now. That volume there, that change in volume is AX. So from that we can see, let's substitute that in, that the work done when a gas expands under constant pressure is equal to, what's it equal to? P delta V. Okay, do we get that? Is that pretty nifty? I quite like that. Okay, so very important that we understand constant pressure. If that pressure is not constant, if it's some sort of function of time or a function of something else, this all gets really, really complex, and you won't meet stuff like that until you study at degree level. Okay, so that's how we get to that formula there, and we can just apply it as long as we know the change in volume. Okay, so enjoy, think about it, and at some point later on, we'll be back with some questions.